So as I said, welcome back, and we're going to have two talks before we break for lunch. And this was supposed to be, are you still, is this still okay? Yeah, all right. So we were planning for you to learn a little bit about NLP, but our colleague Mayank is at IIT Delhi today. So unfortunately, he's stuck with trends in theory. And this is like, I don't know, everyone's heard the story about the student who had to prepare for an essay in an exam, and there's only one topic that he learned about. And then when he went to the exam, of course, it was a different topic. So he spent a couple of sentences writing about the different topic and then tied it to the one that he had learned about and then went on to write about the one that he had learned about. So this is going to be a little bit like that joke where I don't know a whole lot about all the trends in theory. I'm going to talk about just one of them, which is to talk about beyond worst case computation. So I'm going to sort of assume that everyone's seen some kind of algorithms and they're aware of paradigms for analyzing algorithms. And you know that typically a lot of us fall back on worst case analysis. Is this a reasonable assumption to make? Anyone want sort of a quick overview of what I mean when I say worst case, or is this good? Okay, so it's important to talk about what happens beyond the worst case, especially when the worst case is really bad. And that's what I'm going to talk about mostly. How do you deal with a situation when the problem is hard? Most of you have probably done a course in algorithms. What are some of your favorite polynomial time solvable problems? Let's make a list. What polynomial time algorithms have you seen? For what problems? Like maybe minimum spanning tree. Okay, you must have seen a few problems. Sorry? Sorting, okay, excellent. Sorting, yes. Sorting, say, a set of numbers or any set of objects that you can compare. It's a great place to start. What else? Okay, you've hopefully seen a bunch of problems like sorting, closest string, spanning tree, longest common subsequence. I don't know, checking if a graph is bipartite or not. I don't know, maybe you've seen things like checking if a two-sat formula is satisfiable or not, stuff of that kind. Okay, but so I was hoping that we will get very few problems so that I can make the point that there aren't very many problems for which you have polynomial time solutions, but the situation is not that bad as seems to be now. So there are a bunch of problems. You can pick up your favorite algorithms text. This could be CLRS or Kleinberg-Tardosh or whatever, and you will find a whole bunch of problems that can be solved in polynomial time. But there's kind of a big bad world of problems out there that can't well, I shouldn't say that they can't be solved in polynomial time, but the best I can say is that nobody knows yet how to solve these problems in a similar fashion using some of the techniques that you already know. So I'm just going to continue the story in the morning. You've landed your dream job, and you know, this is day one at your dream job. And instead of analyzing data, a slightly different story. So you're given a map of the road network of the city, and you're told that you are sort of making plans. Maybe this is a new city or they're revamping stuff, and you need to figure out placements, good locations for petrol bunks or gas stations. So you need to find places where you can install these petrol bunks. You can only do it near intersections. And there are two constraints. One is a budget constraint. You only have so much money, and so there are only so many petrol bunks that you can afford to install. The other constraint is that you want these petrol bunks to be conveniently installed so that if a car is stranded on a road, then the car can go to at least one of the endpoints of the road and you know, find a refill or get a repair or whatever it is that they need. Yeah. So is the situation clear? This is what your boss explains to you, and so you need to find. So this in graph theory is what is called vertex cover, and so your task is to find a smallest sized vertex cover. Smallest size because you're constrained by the budget. So maybe not strictly speaking smallest size, but can you find a vertex cover of size at most K, where K is your budget? So you can afford to install only K petrol bunks. So can you find a vertex cover of size K in this road network? Yeah, is the situation clear? Yeah, and your response is going to be like, what the hell? Where do we get started? You could, I mean, I'm going to fast forward the story, but you could spend a few days thinking about this, and you will not be able to impress your boss with a fast algorithm that solves this problem. You could try to solve it by hand somehow, but assuming that this is a big graph like Anirban was saying in the morning, maybe millions of points. I mean, okay, a road network will probably not have millions of intersections, but very many of them. So many that you're still going to have a tough time doing it by hand. Yeah. So you're unfortunately a bit lost. And in the lecture in the morning, we saw we saw that we actually did come up with some clever strategies. Now, on the other hand, we're going to cheat a little bit, and this is going to sound a bit strange. So the backdrop of what I'm going to talk about is the fact, or this idea, that we believe that some problems are genuinely harder than others. Okay, they're intrinsically more complex. And so the high-level classification that we've come up with is a class that we call NP versus a class that we call P. So the class P contains all the problems that you're familiar with from CLRS or wherever you studied them from. And these guys have nice, efficient algorithms. NP is the rest of the world for which the verdict is still out, and we don't really know much about what's going on here. Among problems that are just out there that we don't know much about, there are some that are particularly annoying and have a lot of baggage and history, meaning that they're famous problems that a lot of people have tried to solve, and they've not had any luck so far. And there is a way in which we can make this definition precise, but I don't want to get into it. Let's just call these problems NP-complete, and they're really the especially hard problems. So instead of solving vertex cover, here is what you are kind of going to do. As I said, it's a bit of a cheap trick, but you're going to go to your boss and tell them, I wasn't able to solve this problem, but neither can all these famous people. That's how you justify your situation. You say that, okay, I can't solve it, but it's not because I'm stupid. It's because the problem was actually difficult. Okay, and the way you do that is this is your problem. Okay, let's say X in this case would be vertex cover. And you go to the library, look up the right books, and find one of these problems that a lot of famous people were not able to solve. So one such famous problem is the traveling salesman problem. How many people have heard about this one? Okay, so then maybe the joke in the beginning was, sorry, a little bit lost. So look up traveling salesman if you want to figure out the cartoon in the beginning. But yeah, the traveling salesman problem is a problem involving, of course, a salesman who travels. There's N cities, and he needs to visit all of them, and he knows the cheapest ticket between every pair of cities, but he needs to visit every city exactly once, and what's the cheapest way to go everywhere. So maybe a familiar problem from your real life, if not something you've seen before. And again, nobody expects to figure out the cheapest store in polynomial time. No efficient algorithms are known, although there's some very interesting approaches. So again, if you haven't seen this problem, you're in for a bit of a treat if you look it up and explore more. But what are you going to do? What you're going to do is this perverse, twisted algorithm. You're going to still come up with an algorithm that actually solves not vertex cover, but solves TSP. Okay, so now again, you may be a little surprised by this approach. Ek to, why are we solving TSP? It was not even our assignment. And secondly, vertex cover, at least I don't know what is going on. TSP, I know for sure, is this famous problem. A lot of smart people have broken their heads on it, and there is no possible solution. So why should I even expect to be able to come up with a solution? Okay, but here's the deal about the way you're going to go about this. You're not going to solve TSP using just the techniques that are known there in the real world, but I'm going to give you one additional sort of magic wand in your toolkit, and that is an algorithm that solves the vertex cover problem. Okay, it's a hypothetical algorithm. It's the thing that you're looking for, but you're not able to come up with. You spent your entire first month at the job trying to solve this stupid vertex cover problem, and you haven't had any luck. Okay, so you're going to say, okay, enough is enough. Let's just assume that not me, but the next person who gets the job after I'm fired manages to solve this problem. And suppose this is how they do it. So this is a black box algorithm. You don't know how it works. But you're going to say, okay, let's do this thought experiment. Suppose somebody can solve vertex cover, right? I'm going to assume the existence of this algorithm that solves vertex cover in polynomial time, and I'm going to use it as a subroutine to solve TSP, okay? And I'm going to feel free to use it as a subroutine because, hey, you're claiming that somebody else can probably solve vertex cover. So I'm like, okay, suppose somebody can, then I have the algorithm at my disposal, and combining it with maybe other known techniques, I come up with this clever algorithm that solves TSP. But now, what do you have? You have this weird implication that if somebody can solve vertex cover, then I can solve TSP. If you show that your algorithm is indeed correct, then this would be very surprising. And in particular, what would be surprising is if somebody managed to solve vertex cover, because if you could, then you could also solve TSP, which people think is very unlikely. Is that line of reasoning kind of clear? Yeah, this is what people call a reduction or a translation from one problem to another. You're kind of saying, you're kind of posing TSP as a vertex cover problem and trying to say that, okay, if you could do this, then you can do that sort of thing. Okay, so this may just about save you from getting fired because it's some sort of an argument for why you aren't stupid for not being able to find the smallest vertex cover or one of size k. But here is an approximate picture of every engineer who works with a real world problem. They aren't happy when they hear this term, when you tell them that a problem is NP-complete, because you haven't really given them any actionable information except for some excuse for why you aren't stupid. Yeah, is that clear? The algorithm that you came up with in the previous slide is not a real algorithm. It has inside it a black box that nobody knows to implement. And in any case, it doesn't even solve vertex cover. It solves TSP, which your boss doesn't care about. So none of what you said is useful. It may just about save your job, but it's not useful. So, so we want to fix this situation, and we want to, just like we did in the morning, come up with approaches that are good enough, even though we know that we can't, even though we know that solving the problem is probably a little elusive. The reason this is an important thing to think about and talk about is because, as I said, there are very many NP-complete problems. I challenged you in the beginning to come up with some polynomial time problems. There are a few, but if you manage to make a list of NP-complete problems, you will find that there are very many of them. And each one of these is a relevant real-world problem that people are interested in solving. Okay, so there is an entire book by now, multiple books and compendiums of NP-hard problems, real-world, relevant, interesting problems that are NP-complete run into the thousands, problems that are mathematically known to be NP-complete that may or may not be interesting in the real world. There are literally an infinite number of them, like literally. So as I said, there are very many of them. One thing that works somewhat in the real world is this concept of a heuristic, which is that, okay, you try to do whatever makes good sense, even if you can't prove anything about these approaches. So these are usually called heuristics. They work reasonably well if you're lucky, but the point is that any notion of coming up with a high quality solution, an optimal solution, goes out of the window because you don't really know how to analyze heuristics. If you go to somebody who's making a heuristic and utter a phrase like formal analysis, they're going to not be able to understand what you're asking for, okay? Because usually heuristics and formal analysis are traditionally just, don't go well together. That's the whole point of a heuristic, is that you do something that seems natural, but you don't really justify it formally. So what we're going to try and do is figure out what are good compromises that are actually backed up by science a little bit, okay? So what we're going to do is start with understanding the situation we are in, which is that we only have polynomial time, okay, because we're interested in being feasible. And we want to work backwards from there to figure out what's the best we can hope for. So the first kind of compromise is that we do the sort of things that we were doing in the morning. We look for approximate solution, we invoke the power of randomization, and we say, well, this may not be the best, but it's going to work most of the time, kind of, sort of. And you actually come up with bounds, like remember we said at most 4 times n and things like that. So you come up with actual bounds, saying that you're definitely going to screw up, but not by much, okay? So that's one sort of approach. If you can't afford to make mistakes and you can't afford to be off from your budget or whatever the situation is, then the sort of thing that you look for is to see if there is something more about the input that you can exploit, okay? So for instance, so the field is called parameterized and exact algorithms, if you want to go and look it up. But so chromatic number is again a famous NP-complete problem. I don't want to go into what it is, but it's something that's hard. If you're just given, if somebody just dumps a graph on your desk and asks you to find the chromatic number, then you're going to be lost. But if that graph happens to be something called an interval graph, if it has that structure, then you can do it in polynomial time. If it's a planar graph, meaning it can be drawn on the plane with no crossings. For instance, your road network is a planar graph, usually. I mean, unless there are highways and underground tunnels, but still, there's not going to be too many crossings. Usually, road networks are almost planar. You can solve chromatic number, again, more or less in polynomial time. Terms and conditions apply. I don't want to get into it right now, but this is something that you can do. Class of graphs called bipartite graphs, again, chromatic number is easy by definition. So if your graph is special, there's something that you can do. You can also do brute force and try to control how bad the exponential time is. So that's the field of exact algorithms. And good solutions tend to not be just one of these things, but a combination of a bunch of different approaches. And I'm going to continue illustrating this through Vertex Cover. Okay, so let's recall the problem. You're trying to find a subset of vertices that essentially ensure that every edge is covered. Yes, so for every edge, one of its endpoints is chosen in your subset. I just want to pause here to make sure that everybody understands the problem. Or is there anything about this that's not clear, or maybe you've not seen a graph before? Anybody in that situation? Okay, all right. So you guys help me come up with some sort of an algorithm. First, let's try approximation, because we've already seen the spirit in which we do approximation. We know that every edge has at least one of its endpoints in the vertex cover. So does that naturally suggest an approximation? So for every edge, I know that the best possible solution, no matter how cleverly somebody found it, and no matter how intricate the solution, it must contain at least one of u or v given the edge ub. Okay. You're not clever and you don't know the optimum, but is there something that you can do while saying that, okay, I'm not going to stray too far from the optimum? And in particular, let me give you a hint by saying that I want to be at most 2 times the optimum, at most 2 times the best solution. So what should I do? Okay, so I take the edge, I take any edge that's still available in my graph. To begin with, I have the entire graph. So I take this edge and I pick both of its endpoints in my solution. Okay, So I know that opt must be picking at least one, I pick both, okay? So I'm suffering probably one extra vertex that I shouldn't have taken, okay? But this is still fine if I'm allowed to be at most 2 times opt, okay? So here's like one way that this could go. So I pick my favorite edge in the graph and I pick both of its endpoints. And once I pick both of its endpoints, notice that I can delete all the edges that are incident to these endpoints because these edges are covered. Okay, I don't have to worry about them anymore. Now in the remaining graph, I go and pick an edge again, and then I sort of repeat this process, and I keep going as long as I have edges to pick. I could stop when every edge is covered, but here I'm actually stopping prematurely because I just noticed that my graph became a bunch of paths. If your graph is a bunch of paths, then finding a vertex cover is easy because you pretty much pick the alternate vertices, and that's the best that you can hope to do, okay? So again, exploiting structure, just watch out for if your graph becomes simple enough that an idea emerges, then use it, right? So that's, you can show that this is sort of a 2 approximate vertex cover always, and the orange edges are what we call a matching. So, so a vertex cover is always at most twice the largest matching, okay? Now let's just take stock. What you do with the matching algorithm is that you always return something that's at most twice the optimum. Now let's get back to the decision question, which is I'm giving you a budget K and I'm asking you, is there a vertex cover with at most K vertices? Okay, even without worrying about the K very much, what is a natural heuristic for vertex cover? Which vertices would you like to pick in your solution if you were just driven by common sense? You're trying to kill every edge using vertices that you pick. Sorry? Vertices of high degree, is that what you're saying? Vertices that cover a lot of edges seem to be like they're good for you, right? Because if a vertex is incident to a lot of edges, so if there are many, many roads that are meeting at an intersection, it seems to make good sense to place a petrol bunk there. And you can actually come up with examples to show that this may not be a good strategy. But it's surprisingly hard to come up with an example where you show that the strategy fails miserably. You can come up with an example to show that the strategy fails, but you'll see that usually in your examples, your strategy fails, but just about. It's off from the best possible solution by maybe like a +1 or a +2. But actually the strategy can fail pretty badly, not just +1, +2, but plus maybe, it can be off by some function of n, but that's not an easy example to come up with. So that's a puzzle if you want to go back and think about it. But it does seem to hint that maybe there is something going on. Maybe this is not a bad heuristic after all, because it's just so hard to come up with counter examples. So it's so hard to make the heuristic fail, although it does fail. But is there a way in which we can formalize this heuristic and make it a little more reasonable to analyze? So that's where having the K is handy. So the question you're asking is there a vertex cover that uses at most K vertices? Now, instead of just saying that I'll pick a high degree vertex, is there a more formal statement that I can make? So if a vertex is degree more than what, it must belong to any vertex cover of size at most K. What's the threshold? So fill in the blank. I'm saying if a vertex is degree at least dash, then it must belong to any vertex cover of size at most K. Okay, without getting into n, so you're looking for a vertex cover of size at most K. Right, so if a vertex has degree, let's say more than K, right? If a vertex is degree more than K, then you're compelled to pick this vertex in your vertex cover. It's not a matter of choice anymore. Because if you didn't pick this vertex, who is going to pick the other guys, right? Who is going to cover the edges that are incident to this vertex? It must be the neighbors, but this guy has more than K neighbors, that's out of your budget, okay? So if you have a vertex with more than k neighbors, then this is pretty much forced in any solution that you're looking for. So basically what you do is you keep discarding vertices whose degree exceeds k and adjust your budget so that you're left with an equivalent instance. Now I claim that after you've deleted all the high degree vertices, the graph that you have is kind of nice in the sense that it is small. It's small if your budget is small. What do I mean by this? So first of all, once all the high degree vertices are gone, any vertex can only cover k edges or less, because if it could cover more, then you would have gotten rid of it, right? So let's say k is the current budget, so any vertex is degree at most k. How many edges can this graph have if it does have a vertex cover of size at most k? So let's assume that let's give this graph the benefit of doubt and say that, okay, maybe you're a nice guy, you do have a vertex cover of size at most k, but look, every vertex that you have can cover at most k edges, not too many. So what happens if I have more than k square edges in the graph? If you have more than k square edges in the graph, then you cannot have a vertex cover of size k. Because suppose you did have a vertex cover of size k, then each of those k vertices in the vertex cover can only cover k edges each, right? And even if all these edges were distinct, which they need not be, so if you have an edge between two vertices of the vertex cover, then you're kind of billing it twice, which you shouldn't. But in any case, even if every edge covered, every vertex in the vertex cover covered k distinct edges, even then the number of things that they can altogether cover is at most k square, because you only have a budget of k for the number of vertices in the vertex cover. And because you have systematically eliminated all the high degree vertices, each of these vertices can only cover k edges at a time. So if your graph has too many edges, then you know that this is already a bad instance, and you can go back to your boss and tell him, look, this vertex certainly does not have a vertex cover of size k, so either increase my budget or relax the constraints, like I won't be able to cover every edge, okay? So that's a fair thing to say, okay? But if that's not something that you're able to say, then notice that you're in a situation where your graph only has k squared edges, okay? And you can convince yourself that if the graph only has k square edges, it sort of also has only k square vertices. Any graph with a certain number of edges has at most 2 times that many vertices, unless you have some isolated vertices, which is to say vertices with no edges incident on them, but you can forget about those for the vertex cover problem. So basically the idea is that, that if you have lots of edges, then you can't have a small vertex cover. Otherwise, you only have very few edges, which also means that you have very few vertices, which means that your instance itself has become very, very small. And then you should be able to run your favorite brute force algorithm and sort of get away with it. So this is kind of the basic idea. And if you really want to, if this problem attracts your attention at all, then I encourage you to go to or Google PACE 2019, PACE. This is the Parameterized Algorithms Experimental Challenge. Maybe I'm messing up how the acronym works, but this year they're running a contest right now. And this contest is about vertex cover. It's about the vertex cover problem. You're given 100 instances of vertex cover. The average sizes of these instances is about 15,000 vertices. So it's not big data big, but it's still pretty big. And the goal is to find the best vertex cover, okay? And they have a live leaderboard. You can see people who have submitted so far, and you can submit your own solutions. So I strongly encourage you to check out the contest and think about participating in it, because this is a nice problem. It has a lot of real world applications. I gave you a toy story about petrol bunks, but more seriously, people who work in computational biology are very interested in this problem. People who work in numerous other areas are interested in this problem. In fact, if you search for it, you will find a lot of code that solves vertex cover coming from not computer science departments, but from labs of other departments who are interested in this problem. So again, if you hopefully remember it, PACE 2019, PACE, just Google the PACE challenge and hopefully you will have some interesting homework to look into. Okay, so I'm just going to summarize the cheat sheet for addressing hard problems. So heuristics are basically driven by common sense. You could do approximate solutions. I didn't talk about it, but you could also randomize. So for every edge, for instance, you could toss a coin to decide which endpoint you're going to pick, and this turns out to be something that has a decent error probability. You can run this experiment a few times, and you will have an optimal vertex cover with reasonable probability. And the other thing to do is to exploit input structures. So these are some of the things that you can do, make the engineers happy, and also feel good about actually solving problems rather than delegating the hardness of your problem to some other problem. Okay, I'm slightly short of time, but I'll still tell you a story about why NP-hardness is kind of fun to work on. Has anyone played this game, Two Dots? Okay, anyone played Candy Crush? And willing to confess to playing Candy Crush? Okay. So I don't know if enough of you know about it, so I'm just going to give a shout out to the field of combinatorial games. I think it's a really cool field to be working in. There is a conference called Fun with Algorithms. It happens every other year. I think it will happen in 2020 next, if I'm not mistaken. You will have to check, but yeah, so these guys work on algorithms for games. And in fact, again, somebody you should probably look up if you have not heard of him is Eric Demain at MIT. He's a computer scientist, and the reason I'm mentioning him in this context is because one of his students at least has written an entire PhD thesis on the subject of the complexity of games. And this includes classic games like Tetris and Super Mario Bros. I'm not sure. Something Super Mario, so whatever. So and actually, if you look him up, you'll also find this course called Fun with Hardness Proofs or something like this. And there's about 20 odd video lectures, and so they alternate between doing traditional problems and problems based on games. So you'll find a lot of these Tetris and Super Mario and other games like that analyzed in these videos. So it's pretty cool. So I was playing Two Dots 2 summers ago. I downloaded it on my phone, and I found that I was spending a lot of my time playing Two Dots. It made my mom very anxious about all the time I was wasting. So so one practical application of the work that I do is that I can justify all the time that I spend playing Two Dots, at least to my mom, saying, no, I'm working on a paper. And I'm trying to prove that Two Dots is NP-hard, which it turned out, fortunately, that it was. But basically, yeah, a lot of these combinatorial games can be analyzed from both a combinatorial and a computational perspective. And it's usually very interesting to do this. What you've probably heard of is AI approaches to game playing. So you've probably heard of some computer brain somewhere playing Go or playing chess or playing one of these things as well as a human, beating humans and things like this. So that's what usually gets the press, and that's a very exciting sort of set of developments for sure. But there's also the more classical approaches where you talk about strategy and you talk about the inherent complexity of a game, which I think is also equally interesting and not completely unrelated to the AI based approaches, because you need to understand strategy, you need to understand optimal ways to play games to help your computers play it well against humans. So I'm just going to very quickly tell you about Two Dots. It's, as I said, I'm spending a lot of time playing this game. So let me just walk you through. It probably looks like Candy Crush. I mean, I've never played Candy Crush, so I'm not really sure. But essentially, you have a bunch of colored dots on a board, and you're allowed to basically kill these dots by, joining adjacent dots that have the same color. So One super move is that if you see a square and you kill a square, then all dots of that color disappear. And you typically have a fixed number of moves. After that, the game is over. And within those many moves, you have to meet a certain set of goals. Like you have to kill so many dots that are red, you have to kill so many dots that are blue, and so on and so forth. Okay. Again, this is just such a simple thing to say, so I'm just going to try to say it in 5 minutes and then I'll wrap up. Just like vertex cover, clique is another graph problem where you're trying to find a subset of vertices that are mutually adjacent. And again, you may have heard about cliques in the context of things like social networks where the term is usually communities. You're trying to find subsets of people that are close knit, that interact with each other a lot and things like that. So communities are not strictly speaking cliques. Maybe not everybody knows everybody, but pretty close to that. So cliques are some sort of an approximate notion of communities and social networks. So given a graph, there's a lot of interest in finding large cliques, which is subsets of vertices that are all mutually adjacent. We don't really have a serious clique here, but if I change the graph, this is an example of a clique. Okay, so the point is that I can do, so I just wanted to give you a concrete example of the vertex cover to TSP circus that I was saying you can do before. I didn't tell you how to actually do something like that. So here is a concrete example. So suppose you want to write a solver for 2 dots, given an n by n board and given a set of goals. Find if there is a set of moves that leads you to achieving those goals in the stipulated number of moves. And here what I'm going to do is I'm going to basically say that you can solve clique if you can solve 2 dots. That's the connection that I want to make. And the way that I'm going to do that is to say that, okay, suppose you have an instance of clique, so you have a graph. I'm going to set it up. I'm going to sort of encode the graph into a board of 2 dots. And then I'm going to feed it into anybody that claims to solve 2 dots. And if you can solve 2 dots, then the way you solve 2 dots will give me several signals from which I can actually recover the existence of a clique from a graph. So that's typically how you make that connection and establish that it's unlikely that you'll be able to solve your problem in polynomial time. So here's how we're going to set up the board. We are going to have a color for every vertex. And I'm going to put in these sort of squares for the vertex colors. And as you can see, they're surrounded by 2 blue dots. Don't worry about the gray ones. You can assume that they're all distinct colors and dummy colors, and they don't get involved in the goals, so you never touch them, basically. There are better ways of doing this, but this is the simplest to explain. And then what we are going to do is, so notice that if you kill that square, the blue guy, the 2 blue dots get connected and you will be able to kill them. So what I have on the top right is a goal which says I want to kill 2k of the blue dots. So you will need to kill at least 2k squares. Is that clear? Yeah, so the goal says you need to kill 2k blue dots, so you need to kill at least k of the squares. And then what I'm going to do is that for every edge in the graph, I'm going to introduce a board that looks like what's there on the bottom. So the colors corresponding to the 2 endpoints of the graph, they're going to sit next to each other. And notice that if I did the square move on U, the blue dots get connected, but simultaneously these red guys also come together, because remember I said that if you do a square move on a color, all dots of that color get destroyed, right? So this causes the red dots to fall. So basically, if I kill 2 endpoints of an edge, then I get 4 of these red dots to line up, okay? So again, I'm maybe going through this a little bit quickly, but you can convince yourself that if I set up these goals 4 times k choose 2, k choose 2 is the number of edges in a clique of size k, then basically the only way that you can meet this goal in 2k plus k choose 2 moves is if you were killing squares corresponding to a clique, okay? So if somebody can solve this 2 dots instance, in particular if an algorithm can figure out if you can meet these goals in the stipulated number of moves, then basically what you have is also an algorithm that solves the clique problem, because you take an instance of clique, which is a graph, and you create this board and you create these goals based on that graph. And then you ask the two-dot solver to solve this particular board. And the way the two-dot solver will do it will tell you if there is a clique in the graph or not. So this is, I just wanted to share with you an example of how you change one problem to another. And this gives you the starting point to maybe come up with approximate solvers for two dots, or maybe randomized ways to solve two dots and so on. So, I mean, if you're interested, you can find this paper online, and there's a couple of other reductions, and there's even a follow-up paper, and there will also probably be more follow-ups. So the Candy Crush papers are also around. People have worked on Candy Crush. They've worked on, how many of you have played 2048, 1024? These games that went viral some time ago. Awesome. So, so there's a whole bunch of papers about that as well. There's a lot of cool things that people have figured out about some of these games. So if you like playing games and if you need a legitimate excuse to keep playing them for very long periods of time, then you should look into working in combinatorial games. That's it's actually a pretty it's a pretty current field. A lot of people are working on some of these things as we speak. And I'm going to pretty much leave you with that. I have a few other things, but I'm, in interest of time, going to skip right through them. And so thanks very much for your attention.